dependency symbol, the author did. I'm not sure they intended to do that, because you've got independency symbol that you place here, but we're really not having to place it on this. Okay, but it's discussed under this title, so it's kind of a little confusing. You know, you look and there's no I symbol, but that's what we're talking about. So axis straightness can also be applied on an MMC basis, and we see that in this chart where we say at max material condition, okay, we need to hold maximum amount of straightness. Then as it departs from MMC, we're allowed to increase. Wow. Man, this thing can turn into a horseshoe. You know, 0.45, half of a millimeter almost. So that they've put this in here this way to show you the extreme that you could run into. All right, normally, as it states here, normally the straightness tolerance is less than the size tolerance. Okay, normally the straightness tolerance is less than the size tolerance. Okay, so in this case, the straightness tolerance can be greater than the size tolerance. Now they're talking about, you know, the calculated straightness tolerance. Okay, so here we are at 0.45. So plus or minus 0.2. You know, so 0.4 is the tolerance on the size, but the out of straightness is actually becoming larger. So something, you know, that may be really unacceptable if it's applied that way, you know. So we have to be careful on. They're showing us that it can go either way, and you may run into it either way. But our application of it, we have to think about the acceptable boundary, the possible condition that it will be in using this kind of specification. So 6.2, so if we produce at MMC 6.2, it's at 6.25. So you can see the virtual condition stays the same. But considering it as a, you know, a cylinder, a round part, an envelope that has to accept this part, mating part that might have to accept it, is actually, you know, going to have to allow for this virtual or acceptance boundary. So the mating part has to be, the hole that it's going to fit in has to be specified and a chart worked out to see if these conditions are going to allow it to go together and fit the way we want it to fit, you know, as far as a sliding fit or running fit and so forth. That's the curse and the beauty of using geometric control. You know, we allow for it. Okay, before we just didn't. With conventional tolerancing, we don't worry about it. Hey, it's got to be this size, and the hole's got to be this size. It should, all of them should fit if they're made that way. But if you know your process could possibly turn out parts that aren't straight just because of the way they're manufactured, then you have to start applying straightness control to both mating parts so that you can allow for that out of straightness and accept it, you know, use it. If your machine has been tested and it shows that it, you know, has greater control, you know, you can lessen up on your straightness. Okay? So, you know, 182 shows the range of crookedness, bending, that out of straightness that you could have, you know. And so your 6.25 is the same, but look what kind of shape it can be in. You know, it's pretty crazy. You know, I mean, they're exaggerating here a lot because that's a whole lot bigger what they're showing. It's less than a half a millimeter with that little diameter there. Proportionally, they've made it larger than if this is really 6.25 millimeters. You know, that's a whole lot bigger than a 0.45 of a millimeter, you know, proportionally. So they're just exaggerating things, you know, to prove the point and how it works. Okay? All right, unit straightness then just breaks it down per unit, you know, per length, and you're saying it has to be straight in this area, right? Notice they're exaggerating here and showing us that overall there could be a kink in the part. There could be that you have to allow for that. You have to be careful that you don't leave off a whole length straightness that should control it overall. And you have this situation where you have mating parts on the shaft, and it needs to be really straight into certain areas where things are going to attach to the shaft, and the rest of it, you know, is minimal control. Not too worried about it, as long as it's really straight in that area. And of course, we carry that over to prismatic or rectangular features, just working off of a median line, okay, a virtual median line for our tolerance zones. Okay, then straightness of a flat tolerance, straightness of a flat surface, okay, are applied as you see on 184, and when you place the straightness control, it's parallel to the view where your geometric tolerance is given, and yes, you could have opposing, or not opposing, but different geometric tolerance in each direction. It's a smaller surface, so we got in this case, it's a good example because we got tighter control on the straightness. Okay, whereas here it's longer, so we can have a little bit more out of straightness and still be a good part, apparently. So that's pretty normal. Shorter surface, tighter control. All right. Then we may just control it on one end of a part, and we identify it. They're showing a center line, a thick center line. So I think that just turned out wrong for them. I'm not sure. I was thinking a chain line, I guess, is a thick center line. Yeah. Suddenly I was thinking it was to be like a phantom. That a chain line was a phantom that was thick. I may be wrong in my memory. I have to go back and verify it in the old manual to be sure. Okay, then we move into flatness, and has to be, the flatness tolerance must be less than the size tolerance when the surface is associated with the size tolerance. Okay, so now we can, a little more restriction when we're talking about flatness. And it doesn't reference a datum, and it's always RFS. Fairly easy concept on it. Two parallel planes, perfectly parallel to each other, creates the flatness tolerance zone, and it's again related to itself. Okay, the size will dictate where it will start. Okay, its maximum outside, and then the flatness is within that perfect form boundary. And then where we want to exceed it, again, we can apply the independency symbol. We put it on, again, on the actual size, saying that this size is independent of our geometric control. So therefore, flatness can go outside of it. Okay, so I found it interesting they would use a curved part here for flatness, but you know, a lot of times we're looking at a flatness as an up and down mountainous terrain kind of what we're checking for, but it can also be just curved or like a sine wave as well. It can come all kinds of shapes depending on how it's manufactured, but it's over the whole surface, but the geometric form is two parallel planes. Okay, flatness applied to size dimension. This is where the derived median plane must be within two parallel planes that are spaced equal. Okay, so we actually apply the flatness to this size, and it actually means that the median plane has the geometric control applied to it. It's a very unusual, because I can't reach inside and find that